Welcome! In this video you will see how inversion of linear transformations is related to matrix inversion. Let's start by looking at inversion of transformations. Because this is a course on linear algebra, I will restrict myself to linear transformations, although the concept of inversion is also defined for nonlinear functions. Here we go. Suppose that t is a linear transformation from Rn to Rn. A function s from Rn to Rn is an inverse of t if the following holds. First, s of t of x is equal to x for all x in Rn. And second, t of s of y is equal to y for all y in Rn. The first requirement means that if you start with any vector x in Rn, apply t and then apply s, then you get the same vector back. Similarly, the second requirement means that if you start with any vector y in Rn, apply s and then apply t, you get the same vector y back. So s and t undo each other's actions on vectors. The main result is the following. Let t be a linear transformation from Rn to Rn with inverse s, then the following statements are true. First of all, s is unique. This means if t has an inverse, there is only one. We can therefore speak of the inverse of a transformation, and it is common to denote it like this. The statement is actually also true for nonlinear transformations, but that's not the case for the following statement. If t is a linear transformation, then s is a linear transformation too. That means that s has a standard matrix, and this matrix has the following property. If t has standard matrix A, then s has standard matrix A inverse. The proof of this theorem is not so hard, but it is a bit of work. Therefore, I would like to postpone it to a later moment in this section. Rather, I'd like to illustrate the theorem with two examples. Let's first look at a linear transformation that you encounter throughout the whole course, the rotation around the origin in the plane counterclockwise by an angle alpha. This is a linear transformation with standard matrix shown here. What can we say about the inverse? Well, geometrically it's clear what it should be. You can undo the rotation simply by rotating back. That is the only way. The inverse is unique. Rotating back comes down to a rotation over an angle minus alpha. So indeed, the inverse is a linear transformation. You get the standard matrix by simply substituting minus alpha in the matrix that we saw before. Now the last part of the theorem tells us that there is another way to find the inverse, by inverting the standard matrix of R alpha. Remember the formula for the inverse of a 2 by 2 matrix. If we apply it here, we get this result. Since cosine squared plus sine squared is equal to 1, we find that the inverse has the standard matrix shown here. Are these two matrices equal? Well, remember these identities for the sine and the cosine. From these it follows that the matrices are indeed equal, as they should be. You see that the theorem enables us to relate the geometric point of view, where we use the properties of the linear transformation, to the algebraic point of view, where we use the properties of the standard matrix. The theorem can also be used to detect non-invertibility. Let me show you how. Consider the linear transformation from R3 to R3 that projects a vector onto the x1, x2 plane. This is a linear transformation with the standard matrix shown here. If t were invertible, then the inverse would be a linear transformation too, with the inverse of this matrix as standard matrix. However, this matrix is not invertible. It has a row of zeros, so it cannot be row equivalent to the identity matrix. It follows that t is not invertible, as you can expect from a projection. These two examples are illustrations of the main theorem of this video. You can find the proof later in this section. Good luck with the exercises.